Hello everyone, thank you so much for coming to my talk. I'll be telling you about non-orientable link cobordisms and torsion in Floer homologies. Specifically, I will be telling you a bit about some bounds for the structure of non-orientable link cobordisms between two knots in terms of the torsion parts of various kinds of Floer homologies of the knots. So we will be studying smoothly embedded, not necessarily orientable cobordisms between knots. And so as like a basic quantity about these cobordisms, we'll define the non-orientable genus of a cobordism which we'll write gamma sigma as 2 minus the Euler characteristic of the cobordism minus the number of boundary components. So in particular, if sigma is a cobordism between knots, then this is just going to be minus the Euler characteristic of sigma. So various topologists have studied this quantity for non-orientable cobordisms. So they've given bounds for it for non-orientable cobordisms between two knots and computed things like the minimum genus that a non-orientable surface bounded by a knot can have. But we'll be asking a slightly different question. We'll be talking about the question of, if there is a cobordism of a certain genus, how complicated does it have to be? This is in terms of the minima, maxima, and saddles for a Morse decomposition of the surface. So let me give a little bit of background about this question. For oriented knot cobordisms, in 2019, Juhas, Miller, and Zemke proved an inequality relating the number of local maxima and the genus to the torsion order of a version of knot Floer homology. Our result is going to be basically a non-orientable analog of this, so our inequalities are going to be analogous to theirs, except that in our case, the cobordism is allowed to be non-orientable. We'll be using slightly different versions of Floer homologies to theirs because we're just sort of choosing ones that behave well for non-orientable cobordisms. So we'll be using a version of knot Floer homology and a version of instanton Floer homology that behave well for non-orientable cobordisms. The version of knot Floer homology we'll be using is Osvath, Stipschitz, and Szabo's unoriented knot Floer homology, HFK prime, which is a module over the polynomial ring Fu, where F is the field with two elements. So it was shown by Haofei Fan that unorientable cobordisms, with a little bit of extra data that we'll discuss later, induce maps on this unoriented Floer homology. So we're going to be studying the torsion part of this, which for a knot in S3, we define the unoriented knot Floer torsion order as just the minimum power of N the minimum power of U that kills the torsion part of this HFK prime. The version of instanton Floer homology that we're going to be using is Kronheimer and Mravka's instanton Floer homology with local coefficients, which is denoted I sharp of K. This is a module over a Noetherian domain S, which has a special element P. More specifically, we can construct S as the quotient of the Laurent polynomial in 4 variables over the field of 2 elements, and P is the image of this element that you can specifically construct in this ring of Laurent polynomials. Let me briefly discuss what these elements mean. So the instanton Floer homology is the homology of a chain complex generated by flat connections on a singular bundle with singularity at the link and also at this theta web that can be chosen to be far away from the link. Then the local coefficients correspond to a local system coming from taking holonomy along the components of the link and along the 3 arcs of the theta web, where T0 corresponds to the holonomy along the link, and T1, T2, and T3 correspond to the holonomy along the theta web. So we will be restricting our attention to certain domains S for which I sharp of k is functorial for non-orientable not cobordisms. In order to capture the information we want about these non-orientable cobordisms, we also are going to want to choose S so that cobordisms with more complicated singular bundles also define maps. Specifically, we want cobordisms with singular bundles represented by surfaces omega, such that the boundary of omega such that omega could have non-trivial boundary, and this boundary sort of sits on the cobordism. Specifically, this kind of thing would happen if in S, the image of T0 is 1, where T0 is this, it's sort of the variable that sort of comes from the holonomy along the link. In this case, it can be shown that for a knot K, the torsion part of I sharp of K is killed by a power of P, and so we can define the torsion order to be the minimum power of P that kills the torsion part. Now let me tell you about Marco and my main result, which is analogous to the main theorem of Juhas, Miller, and Zemke's paper. So the theorem says that if you have two knots K1 and K2 in S3, and there's a non-orientable knot cobordism sigma in I times S3 going from K1 to K2, and this cobordism has M local maxima, then for both HFK prime and I sharp, the torsion order of K1 is bounded above by the maximum of the torsion order of K2 and M plus the non-orientable genus of the cobordism. As a remark, the same is true for orientable sigma, but in that case, the inequalities actually follow from the exact same argument as Juhas, Miller, and Zemke's theorem, because the only thing that they actually use about the version of not Floer homology they're using is the tube cutting formulas. But in the orientable case, the versions of not Floer homology and instanton Floer homology that we're using satisfy the same tube cutting formula. And so the only real subtlety in our results that makes it that's different from theirs is in dealing with the non-orientability of the cobordism. So the argument that, let me just tell you now about the argument that we make. So it's going to be pretty, the argument, sort of the setup is going to be still analogous to Juhas, Miller, and Zemke's. And the main difference is that we're keeping track of one non-orientable piece. So like how they do, we start by isolating, by decomposing the cobordism. So it can be shown that if you have a non-orientable cobordism between two knots, with little m local minima, b saddles, and capital M local maxima, then you can decompose this cobordism into a sequence of cobordisms consisting of the little m births, those are the local minima, and then little m band surgeries that cancel these births. Then you have all these b minus m plus 1, these additional band surgeries, which are consisting of bands which are orientable with respect to this knot that you got after doing your births and birth canceling bands. And then you have one band surgery that's unorientable with respect to that knot, and then you have the death canceling bands and the deaths. So this is an image of what's going on. So you start with your births, your birth canceling saddles. These additional saddles are orientable with respect to K1 prime, and then there's one saddle that's non-orientable with respect to K1 prime, and then you have the death canceling saddles and the deaths. So to show that you can just have one non-orientable saddle is that the way you can show this is if you have multiple non-orientable saddles with respect to K1 prime, you can just sort of slide one over the other until you and make them all into orientable saddles. The structure of our argument will also be analogous to that of Juhas, Miller, and Zemke, where we compose the cobordism with its mirror and then add and delete tubes using tube cutting formula. So let me just tell you a bit about how their argument works. So you start with your cobordism, which you've decomposed, And then you compose it with like the same cobordism but run backwards, so like the mirror. Then you basically sort of cancel these pieces bit by using tube addition and cutting. So for each death in the original cobordism, you connect it with a tube to its like the corresponding birth in the mirror, and that sort of cancels that death. Then for each death canceling band and additional band, you cut like a tube, and that sort of cancels those bands. And then like after you've done this, you basically end up getting a map that's essentially like a cylinder on K1, so like which induces the identity. So to control the map induced by the original cobordism, you just need to know how tube addition and tube cutting affect the cobordism. As a starting point, let's talk about tube addition and cutting formulae in the orientable case. So for sigma prime obtained from sigma by the addition of a tube whose feet are oriented equally on sigma, if the feet of the tube are in the same connected component, then in the HFK prime situation, the map induced by sigma prime is U times the map induced by sigma. So adding this tube multiplies the map by a factor of U. In the instanton situation, we actually have maps induced by dotted cobordisms. Those are cobordisms with some extra marked points where these points are oriented. And in general, if I sharp sigma prime and I sharp sigma are the maps induced in I sharp by sigma prime and sigma, where sigma prime is obtained from sigma by the addition of a tube whose feet are at P and Q, then I sharp of sigma prime is P times I sharp of sigma plus I sharp of sigma dotted at P plus I sharp of sigma dotted at Q. So if P and Q are oriented equally and are on the same component of sigma, then these last two terms cancel, right? Because we're working we're working in characteristic 2. So if you look at these two formulae, and then you look at this previous picture we have this cobordism. It's the same as your original cobordism, but with these death canceling tubes. With this cobordism, you could cut capital M tubes, where capital M was the number of deaths, to obtain the composition of sigma mirror with sigma. So if you cut like these tubes, you get these the original composition of sigma's mirror with sigma. And then you could cut B minus lowercase m tubes to obtain something that's basically induces the same map as the cylinder. Basically, it's like the cylinder, but with some extra spheres that don't actually do anything. So because of that, like with these formulae, what you get is that in both the instanton and HFK prime cases, the map induced by sigma mirror composed sigma can be related to the identity, the map induced by the cylinder, because like the map induced by this sort of cobordism that's sigma mirror composed sigma with these extra tubes is like equal to both sides of this, right? Because you cut M of the tube, capital M of the tubes, and you get sigma mirror composed sigma, and you cut B minus M of the tubes to get the identity. So that, and this is true in both HFK and in the instanton case, and then the main theorem just sort of follows from these relations. So this is sort of what you do in the orientable case. In the non-orientable case, all the orientable pieces in our decomposition can be dealt with in the same way as what we just mentioned. So let's talk a little bit about what goes wrong with the non-orientable band and what to do about it. So as a demonstration, in the instanton case, in the instanton situation, what goes wrong with a non-orientable band is that an RP2 seen as a map from the unknot to itself, which is basically like the unknot with a single non-orientable band, induces the zero map in this version of instanton Floer homology and most of the other versions that we sort of care about. And that's sort of already just in itself a problem, because what our argument is trying to do is count factors of P in the maps induced, and if the map is zero, then that makes everything kind of useless. And this is sort of like, I mean, this is what happens just with a non-orientable band from the unknot to itself, like just the very simple RP2, like twice punctured RP2 as a map from the unknot to itself. And so it's sort of also just generally what you would expect to happen, is that you somehow lose a lot of information. So the way to deal with this is by adding some decorations. So in the case of I#, there's like we mentioned, there's a version of I# that that allows you to induce cobordisms not just with like induce maps not just with regular cobordisms, but also with like cobordisms with this extra decoration. And the decoration is a 2-manifold with boundary on the cobordism, such that the this surface meets the cobordism only on the boundary, and there it meets cleanly. So it sort of meets like transversely. And sort of what we actually basically want to do is take this surface, like this sort of decoration surface, which we'll call omega, to be basically like half of a Seifert surface. So the Seifert surface of like half of the knot with this extra little piece sort of sticking out. So what I mean is you can sort of consider this like band, this non-orientable band, which I've sort of drawn here in the middle. And this like outside dotted piece is not really, I mean, it's not, it looks, I've drawn it as the unknot, but it could be any like this complicated piece of the knot. But the important part is this band that we're focusing on. And then you take like this band sort of divides this knot into 2 pieces, and you take just like one piece of this and consider basically a Seifert surface of this knot, and along with a little half disk whose boundary is like a diagonal of this band. So here's sort of another picture of what's going on. So we have like this like pink piece of the knot and the blue piece of the knot, and this like green diagonal just cuts across this non-orientable band. And what we want is like a Seifert surface of the pink piece plus this little like disk whose boundary is the green band. But if we just take this, and then like with this decoration, the idea is that the map on instanton Floer homology induced by this cobordism is no longer going to be trivial. But I mean, there's like a little bit of a problem here, which is that if we just take this Seifert surface and this little piece, it might actually intersect the rest of the knot, which we don't want, because we wanted this decoration surface to only intersect the cobordism at the boundary of the decoration. But that, it turns out, is not actually a real problem, because like, I guess if you can think of it this way, if you have this like Seifert surface, it's of like the pink and green pieces, right? So that's like A and C. And if it intersects like B, which is this other piece, the blue piece, what happens is you can always just sort of unwind it. Like, so you have these intersections, you could have positive and negative intersections, but you can sort of wind B, or like the ends of B, around this AC loop until like the positive and negative intersections cancel out. And then you can just sort of add like a tube to this surface, like whose boundary is A and C, that goes around, like, that sort of cuts out, like if B is intersecting, like goes up and down, you can sort of cut that part out with a tube, so that your surface, like modify the surface by adding some tubes, so that it no longer intersects with this with the rest of the knot, with the B. After writing down this surface, so you have this map, like, so you now consider, instead of considering your original cobordism with its mirror, we consider the cobordism with its mirror with this additional like decoration on it. Then it turns out that like so it basically looks something like this. You have like this non-orientable band and its mirror forming this tube, and then this like decoration just sort of goes through this tube. And this tube sort of, it's not really shown in this picture, but it's sort of, it's like kind of non-orientable with respect to the rest of the surface. So it sort of has this flip, and the decoration, like the boundary of omega, is sort of going down this tube where like there's a flip in the middle. So, and then it turns out that you can show that with this extra decoration, like the map sort of no longer vanishes. It's sort of expected that it no longer vanishes in the case of the unknot, and actually it has a tube cutting formula that ends up being almost the same as the tube, like basically the same as the tube cutting formula in the orientable case. And then you can basically, like, once you cut this tube, like the decoration also sort of gets modified with this tube cutting formula, then the decoration can just kind of go away, and you end up with like, again, the identity map. So this sort of, it mirrors the argument in the orientable case pretty much exactly, just after you sort of pick the right orientation.